Okay, so in this video we're going to take a look at problem number 17 and 18 of the sample final. Number 17 states to write but do not evaluate a three-term Raymond sum for the integral from 0 to 1 of the square root of 1 plus x squared dx. So, first of all, what you want to do is create a sketch of your integral. If you notice, your integral starts from 0 and it ends at 1. So you're looking at this closed interval from 0 to 1. And if you notice, if I want to create my sketch, what I did was I plugged in 0 and 1 into my square root of 1 plus x squared. If I plugged in 0, then the square root of 1 plus 0 is going to be 1. So therefore I have the order pair 0, 1. And if I would have plugged in 1, I would have had 1 plus 1 squared, which is just 2, so it's the square root of 2. So I have the order pair 1, square root of 2. And what happened is that because I'm looking at the square root of 1 plus x squared, if you were to take a look at its graph, it looks something like this curve here. And what we want to do is basically find the area that's underneath this curve, but at the same time, it's above this x-axis, right? When you're dealing with this area, since it's above the x-axis, you know that the area is going to be positive. Now, what we want to do is write a three-term Raymond sum for the integral. So what we have is this following idea here, where the area is equal to the sum from I equals 1 to n of f of xi times delta x. Well, let's just break this down again. Remember, delta x represents the width of your width of each of your rectangles that we're going to construct. So, because you want to construct the width of each rectangle, you can compute it by just taking the difference of b minus a over the number of rectangles. So, since you're looking at a three-term Raymond sum, then you can conclude that you're going to deal with using three rectangles. Now, for the values of b and a, it's the values of your region on that closed interval. A is 0 and b is 1. So what we have is that delta x is 1 minus 0 over 3, which is 1/3. So the width of each rectangle is going to be 1/3, but at the same time, it creates the subintervals for us, right? Remember, if you have this main interval from 0 to 1, your delta x basically splits your main interval into subintervals. And now, because of the fact that our width is 1/3, if we start at 0, then we can construct the following subintervals. We're going to have from 0 to 1/3, then we're going to have 1/3 to 2/3, and then finally 2/3 to 1. So those are going to be my three subintervals. I don't know why it looks a little sloppy, the red ink, but let me just write over it. It's going to be 1 over 3 and 2 over 3. Right? So 0 to 1/3 is one interval, 1/3 to 2/3 is your second interval, and 2/3 to 1 is your third interval. And just remember, this region now is going to get sliced now into three regions. So here's one region, here's the second region, and that will be your third region. Okay, now we just got to figure out what does f of xi represents. Well, f of xi represents the height of each rectangle constructed. Now, if you want to figure out the height of each rectangle, then you can either use your lower Raymond sums, you can use the upper Raymond sums, or you can even use the midpoint. In this case, I'm going to use the upper Raymond sums. You could have used lower if you wanted to, but I decided to use upper Raymond sums. If I'm going to use upper Raymond sums in this case, then for each subinterval from 0 to 1/3, 1/3 to 2/3, and then 2/3 to 1, I'm going to choose the highest value in each subinterval. Now, roughly speaking, my function is increasing from 0 to 1. So, because it's increasing throughout the interval from 0 to 1, then for every right endpoint of your subinterval, your highest value will be precisely at those values, right? So, if you notice, from 0 to 1/3, this first interval that we have, because it's increasing, your highest value will be at 1/3. And because you have the highest value at 1/3, you can construct this rectangle. And that will give you the area of the first rectangle. So from 0 to 1/3, you'll have that the highest value, or the greatest value, is going to be f of whatever 1/3 is. Meaning, when I plug 1/3 into that function, that will give me my highest value. Now similarly, from 1/3 to 2/3, because it's increasing, I can use 2/3 as the value to represent, I can use f of 2/3 to represent the height of my second rectangle. So again, this will be from 1/3 to 2/3. The highest value is f of 2/3. Now, how do I know all of this? That's going to be exactly the highest value? Well, the function's increasing, so therefore, for every right endpoint that you have, the highest value is going to be located at that right endpoint. Now, finally, from 2/3 to 1, we can see that clearly the highest value is going to be at 1. So I'm going to create a rectangle that has a height of f of 1, which is the square root of 2. So this will be the area of, this will basically be rectangle 3. So from 2/3 to 1, we're going to have the highest value is f of 1. So using all of this information now, I'm now able to estimate the area underneath this curve using these three rectangles. Now, just by the way that our graph looks and the way that our rectangles are formed using our upper Raymond sums, you can see that we're definitely going to be overestimating the total area underneath the curve. But hey, that's fine. We're just writing, but not evaluating this three-term Raymond sum. So, here we go. We're going to have area is approximately going to equal to the area of the first rectangle plus the area of the second plus the area of the third. Now, using upper Raymond sums, we'll have the following. Again, just remember we're not evaluating this, so I'm setting it up, and that will be it. We're going to have that the area, well, let's figure out what would be the area of the first rectangle. Recall, delta x represents the width. Your width is going to be 1/3. So we're going to have 1/3 times the highest value in that first subinterval, from 0 to 1/3. Well, that's f of 1/3. So we're going to have 1/3 times f of 1/3, whatever that is. What is it? Well, what I'll have to do is just take 1/3 and plug it into my function and then try to solve, but that's okay. We could leave that for another day. Plus, now for the second rectangle, its area will be 1/3, right? The width stays the same, times the highest value from that subinterval, from 1/3 to 2/3. Well, that's going to be f of 2/3. plus. Now here, you're going to have, again, the width of 1/3 for your third rectangle. Its height, because we're using upper Raymond sums, is going to be f of 1. And that's it. You don't have to do anything else after this problem. Now, if you wanted to use lower Raymond sums, then you would have had to choose the lowest value in each subinterval. So if you were to use lower Raymond sums, it would have been 0, then 1/3, then it would have been 2/3. But just again, you're setting up a 3-term Raymond sum. It could be upper, it could be lower, it could be a midpoint. I just chose to use upper. And that's it for number 17. Let's look at number 18, and then we'll just have 2 more problems to do in the next video. So, problem number 18, just to fast forward things for us a little bit, I sketched the region already, and now we just have to basically compute it. So number 18 states to find the area under the curve y equals 5 minus 2x squared, right? If you take a look at that equation, it's a quadratic. It's from x equals 0 to x equals 1. And what we want to do is basically find this area underneath this curve that is, again, above the x-axis. So if you notice, this region is definitely going to be a positive result. Just notice that the way that I got the order pairs 0, 5 and 1, 3, I plugged 0 and 1 respectively into my equation. And because it's a parabola that's going to be opening down, I just sort of form like this curve from the point 0, 5 to the point 1, 3. So the first thing you want to do with number 18 is set up your integral. So if we set up the integral here, remember, your integral has to be in the form from a to b of f of x dx, right? That's your definite integral. Is going to be the following. What we're going to have is the integral from 0 to 1, since it starts at 0, ends at 1, right, for our region, of our function, which is 5 minus 2x squared dx. So now, if you want to figure out the area of this region, we could basically apply the fundamental theorem of calculus, right? If you recall, the fundamental theorem of calculus states that if you have this definite integral from a to b of f of x, where f of x is a curve that is definitely above the x-axis, which means that its region's above it, then you can compute the area of the underneath that curve as follows. You will have basically f of b minus f of a, where this capital F is the antiderivative of your lowercase f of x. So essentially, once you set up the integral, you want to apply fundamental theorem of calculus. So I'm going to abbreviate that. We're going to say FTC, fundamental theorem of calculus. So we have the integral from 0 to 1 of 5 minus 2x squared dx. Well, let's integrate. Well, if we integrate this, we're going to have 5x, right? The antiderivative of 5 is 5x. If you take the antiderivative of 2x squared, that's going to be minus 2x to the third power over 3, right? I had to apply my power rule for integration. And now this is going to be from x equals 0 to x equals 1. So now I have to plug in the upper limit of integration first, then my lower limit of integration, and I'm going to take its difference, and that will give me my area. So we have the following. We're going to have 5 times 1 minus 2 times 1 cubed over 3 minus, well, if I plug in 0, everything's here going to be 0, right? 5 times 0 minus 2 times 0 cubed over 3. So we know that this piece, that's going to, oops, it doesn't want to go bye-bye. It's going to go bye-bye because of the fact that 5 times 0 is 0, 0 cubed is 0, so all of that's going to be 0. So we just got to worry about now what is the difference between 5 times 1 minus 2 times 1 cubed over 3. Well, what we're going to get is the following. 5 times 1 is 5. 1 cubed is 1, so we're going to have basically 5 minus 2/3. You can rewrite this as a single fraction, right, where you write 5 as 5 over 1. Find the LCD, which is 3, so you're going to have 15 over 3 minus 2 over 3. Keep your denominator, which is 3, and now take the difference of the numerator. So 15 minus 2 is 13. So your final answer here is 13 over 3. So the area underneath the curve of y equals 5 minus 2x squared from x equals 0 to x equals 1 is precisely 13 over 3. Just again, make a sketch, set up the integral, apply fundamental theorem of calculus, and just do some computations. That's about it.